Hi there. Today we're going to talk about Chapter 11, Confidence Intervals and Hypothesis Tests for Means. To start off, I thought I would start talking about what we first did last week, which was also in Chapter 11. And we learned that under certain conditions that y bar, the sample mean, is approximately normal with mean mu. And standard deviation sigma over the square root of n, where mu and sigma were the mean and standard deviation of the population distribution. So mu is the center of the population, sigma is the spread of the population. We take a sample of size n, and then if that sample is big enough, then the distribution of a sample mean is normal. All right, so the first question I asked, if we have n equals 36 houses, so this is n, what would you expect the distribution of the sale prices to be? So this is not for the mean, this is for the actual sale prices. All right, so sale prices, we would think, okay, here's sale prices of homes. We might say, okay, here's the average house for that house. Here's the average price, and then I might have some that are a little bit less. But we know that there's a minimum of 0 over here, but the houses could get more and more expensive as we go to the right. So we tend to think of things that are limited by 0 on the left and unlimited on the right as being probably right skewed. So we're going to pick that the prices tend to be right skewed. Okay, if we wanted to use the central limit theorem, what assumptions would we have to assume? Well, if my sample, and this asks actually a real estate agent, this is for n is 10. So this is a much smaller sample. For n is 10, we talked about last week, if our sample is between 5 and 15, right, and 10 does fit in that interval. So my sample size is in there, that we need a unimodal symmetric distribution. We think it's probably slightly right skewed, all right? So, but in order for this to be normal, if we wanted to use the central limit theorem, then for this size, they would have to be unimodal and symmetric. So, random, they don't have to be random. They do have to be independent. We have to have independent observations that we believe represent the sample. And then they would have to be not too skewed and without outliers. So those are the two things. So the two conditions, there was the size condition, and there was also that they have to be independent and representative. Okay, next question. Now we're going to do an ask. I'm only going to do one of these. It says, according to a recent poll, 27% of adults have high cholesterol. They report that such elevated levels could be financially devastating to the healthcare system. Okay, so according to recent studies, cholesterol levels in healthy adults from the area averaged 209 milligrams per deciliter. Now, the question becomes, these 209 milligrams per deciliter, is this mu or x bar? Or y bar, we've been calling it. All right, which one is that? So it's an average, so that's the mean, all right? And then one of the ways we can tell is that that's the mean of everybody, or if that's the mean of a sample, is if they tell us how many there are, okay? And this says, according to recent studies, so there's no n in here. There's no sample size in that, all right? So this is going to be, this 209 is mu. So mu equals 209. And the standard deviation, this is the standard deviation of everybody. This is going to be sigma. Okay. And it says that they are roughly normally distributed. So they're already unimodal, and it's unimodal symmetric bell shapes already. All right. So now we're going to look at a sample. Here's our sample size. So now we're taking a sample of n equals 43 people. And it asks us, what's the mean what's the mean of the sample mean. So if I took a sample from this population, where mu is 209 and sigma is 30, so if I took a sample and I, said, okay, what's the average cholesterol for that sample? We'd expect it to be around the mu, okay? So the mu is mu, this is going to be 209. So we'd expect an average cholesterol in our sample to also be 209, just like the population we're taking the sample from. All right, the standard deviation is sigma over the square root of n, and sigma is 30. And the square root of n, that's the square root of 43. Let me put that in my calculator. So I'm going to type in 30 divided by the square root of 43, and I get 4.575. All right. So I went ahead and drew the drawing here. So this is a normal distribution. We think when the sample size is large enough, 43 is a big sample. Actually, since the population distribution is already normal, then a very small sample would also have a normal mean. All right, so the mean is 209. So here's the mean. This is mu. We put mu in the middle. All right, so the distribution for the mean. Goodness gracious. There's some technical difficulties here. Trying to type mu. There we go. So 209 is mu. That goes in the center. And we want to know the probability that's asking is what is the probability that the mean cholesterol for the sample, so this is the mean of the 43 people, that their mean cholesterol will be between 204 and 214. So 204 is less, I put that on this side. 204 is bigger, put that on the right side. And we draw the area in the middle. Okay, so we're going to get a z-score for this guy. Right, and a z-score for that guy. All right, so let's do 204 first. So we're going to get a z-score for this guy. The actual formula is y bar. We subtract the mean, which is mu. We divide by the standard deviation. All right, so the y bar of interest here, we're interested in if the mean is between 204 and something. So it's going to be 204 minus the mean, which is 209. And divided by the standard deviation. Now, we don't want the standard deviation of the population, which is 30, right? Because what we're doing is we're getting the probability for the mean cholesterol of a sample. So we're looking at the sampling distribution, and the standard deviation for that is sigma over the square root of n, which we got is 4.575. All right. So this is minus 5, 204, minus 5 of this. This is actually equal to negative 1.09. Right? So 204, cholesterol of 204 on average is a little more than one standard deviation below 209. Okay. Then to get the one above it. Well, the one above it is 5 above. So this one's 5 below, this one's 5 above. So by symmetry, we know this is going to have the same z-score, it's just going to be positive. So 204 is 1.09 standard deviations below the mean. 214 is 1.09 standard deviations above the mean. So when we get z-scores, what do? We look them up. We do not calculate anything with this. We don't subtract these because z-scores are not additive, but areas are. So we get on the next one. Just rewrite. Here's my 2 z-scores. So what do? I'm going to look these both up. So I'm going to get these two values from the standard normal table. I look up z equals negative 1.09. And if I find that in the standard normal table, I looked it up, it gives me 0.1379. So that means this is about 14%. So about 14% of the area is to the left of 204. Because the standard normal table always gives me the area less. Then I look up the positive 1.09, and that is 0.8621. Again, from the standard normal table. Well, the positive 1.9 was the z-score for this guy. So the 0.8621 is all the area to the left of 214, which includes this white area and this shaded area together. So this area and this area together are the 0.8621. So since these two together equals 0.8621, the area that I'm looking for has to be the total area minus the smaller area. And that ends up being, so this is 0.8621. I'll just subtract the two values I get out of the table. And that equals 0.7242. Okay. Put you on there. So what does that tell me? It tells me that if I take a sample of n equals 43, and that's a sample where the average was 209, and the standard deviation was 30, right? If I take a sample from that population of size 43, then the probability that the sample mean from those 43 adults, that it's between 204 and 214, is 0.72. So the probability that the average cholesterol is between 204 and 214 equals 0.7242. Right. Another way to say it is if I took a bunch of samples of size 43, in 72% of the samples, the average cholesterol would be between 204 and 214. Okay, so that was the homework. 2 small problems. All right, so now we're going to do inference, which is what we study statistics for. And in statistics, we don't take a bunch of samples. We don't know the population mean ahead of time. We don't know the population standard deviation ahead of time. What we do is we take a sample and we say, okay, here I got a sample mean, y bar, and I got a sample standard deviation, s, and we're going to use those as estimates of the population mean, mu, and the population standard deviation, sigma, all right? Now here's the central limit theorem that we just covered, all right, that we talked about last week, so this is review, and we said that the sampling distribution of any mean from a sample, right, becomes normal with mean mu and standard deviation sigma over the square root of n as the sample grows, where mu and sigma are the mean and standard deviation of the population. So let's say, just like we were talking about before, let's say these were house prices. All right, we don't expect house prices to look normal, because normal means it's symmetric. We expect house prices to have a distribution that's right skewed. We have here's the houses in general, and then, okay, as you go to the right, we have a few houses that are more and more expensive, right? But if I take a sample of here I said, okay, here's a sample size 25 for this same data, then the mean from that, so this is the distribution of y bar. So here's y bar, and this is a y. This is the distribution of a house price. If I pick a house price, this is how often a house price would be in certain intervals. This is if I take a mean of a certain size, here I said 25, and now you see the spread is way smaller, okay? So the central limit theorem tells me that the sample mean y bar, gets less variable, right? It gets less spread out. And it gets more normal. So maybe a sample size of 5 wouldn't be big enough for it to be normal. But as n gets bigger, the distribution of y bar gets more normal. As you increase n. As n gets bigger. I'll say as n goes to infinity. N is increasing. Yeah, maybe this. As this increases. Okay? Alright, which is great because I don't know how to calculate areas under this guy. I don't know what these are, but I can get these from the standard normal table, right? So I can calculate normal probabilities. That's great. It's one of the awesome things about the central limit theorem is once if the means are normal, I know how to calculate probabilities about them. Okay, and just recall what the conditions are. The conditions for normality of the sample mean is the same as has the same type of two conditions that we've studied before. We need an independent sample, meaning the observations are independent of each other, the outcomes are independent of each other, and we need a sample that we believe is representative of the entire population we're interested in. Okay, so we don't want convenience samples that leave out portions of the population. We don't want voluntary response samples. Random samples will take care of this. So if I have a random sample, then that by definition it'll be independent and representative. All right, now we need the large enough sample condition, and I mentioned this in the homework when I was discussing the homework. Okay, small samples will not make the distribution much more normal than it was to start with. Okay, so if I have a small sample, it better be approximately unimodal, symmetric, maybe it looks like that. All right, so as long as it's very close to being unimodal, symmetric, here. Then, if I take a distribution, if I take a histogram of the data and it looks like that, then it's okay. But let's say, so this one's okay. Let's say maybe it looks like this though. Then we can't, that's for a small sample. So if my n was, 8, and it looked like that, that would not work. Okay, the distribution of y bar would not be normal because it's only going to get a little bit more normal for n is 8. Okay, but then once I get to 15, so around 15 to 40, as long as it's slightly skewed. So this guy over here, this would work if my sample size was between 15 and 40. So as long as it's at most slightly skewed, anything between 15 and 40, that's going to work. Now, if n is bigger than 40, we call that a large sample, even though it's not that big, all right? But as long as the histogram is unimodal and it's not extremely skewed, so I could have something that's, that's skewed. I have something like this. That's pretty skewed, but it's not extremely skewed. Here's extremely skewed. Or it's got large outlier. Okay, we can't do that one, period. This one, as long as n is greater than 40, we're good. Okay, so those are my conditions. Now, we've got to talk about standard error, right? So I told you we're going to take a sample, all right? We take a sample. All right, we're going to calculate, we'll have n, we'll calculate the sample mean, y bar, we'll calculate the sample standard deviation, s, but I'm not going to know, so I'm not going to know mu, okay, and we're going to do inference on that guy. We're going to say, give me a confidence interval of mu. But I'm also going to not know sigma, all right? So I don't know these things. These are the population parameters. These guys are the sample statistics. So I'm not going to know how the population looks. I'm only going to know how my sample looks like. So I have these sample statistics. Well, I'm going to use y bar as an estimate of mu and s as an estimate of sigma. All right? So standard error, remember we used that in the confidence intervals for proportions, and we said that the standard error p hat was this. All right? And the reason we said that it was the square root of p hat q hat over n, was that the actual standard deviation of p hat was the square root of p q over n. So notice p and q, those things describe the population. And so we're going to estimate those with the p hat and q hat from the sample. Now n is from the sample. All right, so for a sample mean y bar, the standard deviation I already told you was sigma over the square root of n. So here's the standard deviation. So we need to estimate that. I use s as my estimate of sigma. So I use my sample standard deviation as my estimate of sigma, and then I get S over the square root of n. Now that is my standard error of y bar. So S over the square root of n is my estimate of the standard deviation of the sample mean. And now I'm going to use that to do my confidence intervals and my tests. Okay, so let's talk about what happens when we use S over the square root rather than sigma over the square root of n. Remember we did the homework, we had some z-scores. I said, okay, you can get a z-score, you can take a y bar of interest, you can subtract the mean of y bar, which is mu, and you can divide by the standard deviation of y bar, which was sigma over the square root of n. All right, that's a z. That has a standard normal distribution. And it's normal 0, 1. All right, so that has the standard normal distribution. This guy's normal. But when I put, instead of sigma over the square root of n, I put S over the square root of n here. It's no longer a z. It's not normal anymore. It's actually called a t distribution. It's called a student's t distribution. This is y bar minus mu, and I divide by S over the square root of n. All right, this has the t distribution, and the t distribution has a parameter called the degrees of freedom, and the degrees of freedom are n minus 1. So this has the t distribution with n minus 1 degrees of freedom, which I'm going to abbreviate df. So we're going to talk more about what that means. All right, so you don't really have to understand what degrees of freedom are, but what this tells me is that this distribution for this y bar minus mu over S over the square root of n, it's not the same like the standard normal distribution. Like the standard normal distribution is always the same, no matter how big n is. But this guy depends on n. All right, so a bigger sample has more degrees of freedom. All right, so if my n, if I took a sample of 100, then the degrees of freedom are 99. Right? And the more degrees of freedom we have, the more it looks like the normal distribution. Right? So let's take a look here. All right, so this is the t. The solid line is a t distribution. And the dotted line is the normal distribution. Okay, so the z, this guy, this is my y bar minus mu over sigma over the square root of n. And then I have my t, which is the solid line, and the t is y bar minus mu over S over the square root of n. The only difference is whether I use sigma, which is the population standard deviation, or S, the sample. Okay, so you can see the standard normal, this dotted line, it gets really flat once you get past 3 standard deviations. Remember, 99.7 standard deviations occur at 3, so there's very little area to the right underneath here. Same over here, minus 3, you got a little teeny little area there. All right? But the t distribution has fatter tails. So if I said, well, what's the probability of being, if my t was minus 3, if you look, that area is way bigger than the area under the dotted line. There's a lot more. Okay? So the tail areas are bigger for the t distribution than the normal distribution. All right, so let's do an example. All right, we have data from a sample. We have n equals 25 randomly selected customers. I think I changed that. Yeah. No, maybe I didn't. All right, so I have 25 randomly selected customer, and their mean age. So this 31. This is a mean, right? So that's got to be mu or y bar. And this is the standard deviation, so that has to be sigma or S. Okay, there's 2 kinds. Mu is a measure of the population. Y bar is a measure of the sample. How do I know? If it has an n, that's the sample. So here we got n. All right, so this is describing those n people. So then this guy is y bar, and this guy is S. All right. So the standard error of the mean is S over the square root of n, and S let's see, is 9.84 standard deviation of my sample, and n, the sample size, is 25. Right? So this is 9.84 over 5. Let me put that in here. 9.84 over the square root of 25 is 1.968. All right. And here you can see that written out. All right. So my, I've got n is 25, y bar is 31.84 years, s is 9.84 years. Okay. All right, here's the deal. When y bar is normal, so when anything is normal, the chance that an observation was within 2 standard deviations of the mean is 0.95. Now later we learned 1.96 standard deviations of the mean is a better number, but about 2, right? So we think that the true mean is within a couple standard errors sorry about that. Okay. So we think the sample mean is within 2 standard deviations of the true mean mu. Okay. So that means we think the true mean mu is within a couple of standard errors, our estimate of the standard deviation of the sample mean. Now instead of being 2, it's actually going to be a little bit bigger because we got that T star where our tails are fatter. Okay, so it's no longer normal, so we're going to have a little bit more than 2, so it's not going to be 1.96 for the means because it's not normal. All right. So here we go. Here's our formula. All right. So we're going to estimate mu with y bar, and then we're going to plus or minus. Here's my T star. All right. So now instead of a Z star, we're going to have a T star. Oops. Here we go. My T star. The n minus 1 just tells me this is the number, like this little subscript here is the number of degrees of freedom. All right, so that's n minus 1, we already talked about. So we're going to get a T star with n minus 2 degrees of freedom, and then I'm going to multiply that by that standard error, which is s over the square root of n. Okay, so just like the Z star was dependent upon, how confident we wanted to be. If we wanted 95%, it was 1.96. If it was 90, we had 1.654. But this is not a Z star. All right, it's not normal. So in Z's, we use the letter Z to represent normal things. All right, the standard normal. So the T is different. All right, so this is how we get the T star. All right, this is the T table. This is in the tables in your book, and if you kept one of those standard normal tables that I gave you, on the back of it was the T table, and I even told you the very last row you could get Z stars off of. Okay, so for a 95% confidence interval, we use Z star as 1.96, 90%, 1.645. 99%, 2.576. Okay. Now for our example, we had n equals 25 customers. All right. So if we want to get a T star for this guy, we're going to have to look up on 24 degrees of freedom. You can see I already circled the 24. So you can see here I have this column right here. These are the degrees of freedom, which are n minus 1. Okay. And then across here, these 5 values, these are all T stars for a sample of 24, and it all depends on what confidence level you want to be. All right, if we want a 95%, which is typically what we use, we'll use 2.064 as our T star. So T star equals 2.064 for 95% confidence. Now, if we wanted a 90%, we would use 1.711. Right? If we wanted a 99%, we would use 2.797. So we're going to stick with the 95%. Okay? So our T star for this confidence interval is going to be 2.064. Okay, so here I'm restating the example. And now we have a histogram. So we got 25 customers, a mean of 31.84 years, standard deviation of almost 10 years. All right, so here's the histogram. And if I was going to describe this, I would call this unimodal. All right, it's got one mode. This guy right here, so between whatever that is. Oh, make it so hard. But 7.5. Okay, so this would be 30. All right, so between 30 and 37.5, I got a mode. This is unimodal. And this has, a little bit, one more bin on the left is to the right. So I would say this is slightly, very slightly skewed left. Okay. All right, so the first thing I'm going to do is I'm going to check my conditions. All right, so I get the independent and representative condition. All right, so I need independent observations that represent the population. And if you look here, it says that these guys were randomly selected. So that means it meets the end and rep condition. So end and rep, independent and representative is met because of this word random. If it doesn't say random, it's not random. All right? It's either random or it's not. It can still be a pretty good sample without being random. All right? So you can still have independent and representative sample without taking a random sample. Random is best though. All right, so the large enough sample condition. We have n is 25. So we look, and here n is 25 fits in here. All right, so between there. So this says I have to have unimodal and most slightly skewed. And guess what? It was unimodal and slightly skewed left. So that one's met. This was met because it was a random sample. Okay. All right, so now let's do here's our calculation. We checked our conditions, all right? And so I just brought in the stuff that we already knew. We had a sample size 25. The mean was 31.84 years. The standard deviation, S, was 9.84 years. We calculated the standard error was 1.968 years. And then we got our T star for 24 degrees of freedom. So here's our T star. And we just plug that in. So Y bar is the mean from the sample that was almost 32 years old, 31.84 years. We got our T star, which was 2.064. I told you a little more than 2. It's 1.96 for normal, but since this is a T, it's a little bit more than that. All right, and then our standard error is S over the square root of N, and that is 1.968. We already calculated that. And so I multiply those together. I got 31.84 years plus or minus 4.06 years. So this gives me 27.78 to 35.90 years. All right, so when I'm stating this, we usually talk about people's age in whole numbers. So round this to the nearest whole number. This is going to be 28. Round this, so this is, round this one, this is 36. All right, so interpret the confidence interval. All right, so this is for mu. This is a confidence interval for mu, which is the true mean age of all customers. So we're 95% confident the true mean age of all customers is between these two ages. All right. All right, you got to be careful. Let's see here. This doesn't mean that all the customers are within this age. All right. When we looked at the histogram, we saw some were very young. If you look down here, we've got some between 7.5 and 15 years old. And so not all the ages are between 28 and 36, okay? But we think the mean is somewhere between here and here. So that's where we think the average age is, between 28 years old and 36 years old, not all the customers. All right, so you got to be careful in your interpretation. All right, if we can do this with StatCrunch, very easy. All right, so now, like we did stat, that was the same for proportions. We did stat, proportion stats. All right, now we're going to do t-stats. These are all going to be t things. We got one sample. We're taking one sample, and we're interested in the mean of that sample. And we have summary data. We have the mean, the standard deviation, and the sample size. Later on, we're going to look at one with data. With data, I would have the age for all 25 people in a big column. Right? All right, and then I come down here and I click confidence interval. It's, it's default is it's on the hypothesis test. I click confidence interval, hit compute, and here this comes out. All right, so this even tells me, here's my sample error. This is the S over this derivative N. The mean, this is the sample mean, so that's y bar. This is degrees of freedom, that's 25 minus 1. And then I have that the ages are between 28, so around this is 28 to 36 years old. So we're 95% confident that the true mean age is in there. Now, we're not 100% confident. It could be the mean age is 27. We just happen to get a higher sample than normal. Sampling error we expect, but 95% of the time that we'll catch the real mean in the interval that we come up with. All right. Here's another histogram. Can we do analysis on this guy? This guy is unimodal. Let's see, not that one. Modal. And, if it was just here, I would call that thing skewed right. But if you look, there's all these people. There's even somebody out there. There's outliers. So this is unimodal. This is extremely skewed. And I would call this extremely skewed because almost all of my observations were in these 3 bars. Right? So I have to go several bars out to get to the maximum. So there's like a lot of things that's way away from the bulk of the data. So that would be extremely skewed. We might even say it's extremely skewed, or that it has extreme outliers. Either one. In either case, this isn't even good enough. Even for this has 500, right? But we don't do analysis on extremely skewed stuff because we are not sure if 500 is big enough. It sounds like a big sample, but we might need more than that for this to be normally distributed. All right? So we don't do analysis on skewed data in this class. Okay, I already talked about that. All right, so now what about a hypothesis test? All right, so with the hypothesis test, the one sample test, we're going to test if the true mean, all right, the true mean, this is the true guy, this is mu. Is that really different from some hypothesized value? All right, and this is that hypothesized value. Is it far enough away from? Is it significantly different from U0? All right, so let's kind of look at my example. I have a new manager of a small convenience store. They sampled every 30 purchases. All right, that is not normal. That is called a systematic sample, all right, from yesterday's sales. And then they give us, if the mean was mean purchase was $45.26, and the standard deviation was $20.67, is that enough evidence? Is this $45 far enough away from $40 to say we think that the average purchase for all customers is over $40, right? Okay, so there, the mu0 is 40 bucks. Right, so we're going to test whether if the true mean is over $40. Okay. All right, so recall, as far as the math is concerned, that we're assuming that the null hypothesis is true when we do a test. All right, so the null here is going to be that mu is equal $40. Right, so for example, all right, so we're going to, and then what we're going to do, we're asking is the Y bar, which was around $45, high enough that we can disprove the $40, right? And we're using the idea that Y bar is normal if we use sigma, right? So it's normal if we use sigma, and it's a T if we use S, okay? So we have this thing has the T distribution, so this is going to be our test statistic, all right? We assume that mu is mu 0, so we replace mu up here with mu 0, and now I have a test statistic. And this has the T distribution with n minus 1 degrees of freedom if the null hypothesis is true. H0 is the null hypothesis, right? So if mu really does equal mu 0, then that thing has a T distribution with n minus 1 degrees of freedom. All right. So we're going to use that to get our p-value. So here's our example again. We have every 30 purchases. Again, this is called a systematic sample, which are great. These are awesome. Right? We don't use, random numbers to do that. We're getting every 30 people. All right? So it's not normal, but it's a pretty good sample. All right, and here's our mean. These are all from the sample. All right, and let's see. Oh, I didn't tell you n. Let's see, what was n? 20 purchases. All right, so every 30 samples, I messed it up. Ended up being n is, so there's 20 purchases that we're looking at, which I didn't write in there, but I wrote later. Sorry about that. And so this Y bar, this mean, is the average price of these 20 amounts. So this is a Y bar, and this is $45.26. And the standard deviation, that's of those 20 purchases, that's S. And that is $20.67. All right, so first it says, what are the hypotheses? And to answer that, we look at the research question. Is there evidence that the overall purchase amount is at least 40 degrees? All right, we get the alternate hypothesis from the research question. So we're saying, is the overall mean, the real mean, the true mean, the mean of all customers at least $40? All right, and the null hypothesis is just stating, well, the null is that the true mean in the population is equal to $40. All right. All right, let's check our conditions. Again, it's not random, but do we have independent observations? Independence means one outcome doesn't affect another. And so 30 purchases ago, how much those people spent is not going to affect what the current customer spent. So yes, they're definitely independent of each other. And are they representative of all purchases? Well, I mean, the only thing I might say, they should be. I mean, maybe one day it might be representative of yesterday's sales, but maybe to get the average of all sales for the store period, we might want to get a few from other days of the week. Okay, but for now we're going to say for yesterday's sales, yes, definitely representative. All right, and so we got 20 purchases. And the sample size requirement for the mean requires a histogram. So we don't have it, but we would really need to see the histogram for this data. All right, so I don't have it, so we really kind of have to reserve judgment. We're going to go ahead and calculate it, but so the test is valid as long as the histogram was at most slightly skewed. So if the data doesn't look like that, if we have somebody spent, $2,000 out of those 20 guys, and most people spend around $40, then this would be a problem, right? So assuming that is true, assuming that it's only slightly skewed, we're going to do the test, all right? First thing we do is we get the test statistic, which I gave you the formula. T is Y bar, or maybe I didn't. Did I give it to you? Yes. There it is, yes. T is Y bar minus mu 0 over S over the square root n. Yes, I did. There it is. I'm going to plug it in. Y bar is the sample mean. That was the 45.26. Mu0 is the mu from H0, which is purchased was the $40. This is our test value. And then S was the standard deviation of the sample. That's 20.67. And N is the sample size, which is 20. So here's our test statistic. It ends up being 1.138. Okay, so this is not a z-score, so it's not the number of standard deviations away. What it actually is the number of standard errors away. Right, so if I draw my t distribution, just like the z distribution, right, I put a 0 here, and I got my 1.138. Right. Instead of telling me how many standard deviations I am, this is the number. This 1.138 is the number of standard errors, because that's what I got in the bottom. So $45.26 is 1.138 standard errors above $40. So this is a little over one standard error apart. Okay, we're going to use that to get our p-value. All right, and here's the thing: there's no table that has all the values of p-values for each degrees of freedom. All right, so we have to use technology. And then when we look up in technology, I'm just telling you this. So we haven't found it yet, but I'm going to show you how. All right, so that t, we said this guy has the t distribution. All right, so this has the t distribution, and it's going to have n minus 1, which is 19. N is 20. There's 20 people. So with 19 degrees of freedom. And that's W/, that's my shortcut for width. So it's got the t distribution with 19 degrees of freedom. All right, so we're going to look that up. Now the way, remember when we looked at the t table, let's kind of go back. Oh, I haven't shown you yet. Oh yeah, I did. I thought when I did the confidence interval. Where's that guy? Okay, yes. Okay, so here's 19 degrees of freedom. This 1.328, all right. So the thing is, those are the only, for 19 degrees of freedom, I only have 5 values in the table. So I can't really use that to look up the value. The value that I have is not one of these guys. All right. So I need technology to do it. All right. So what do I do? Okay. Let me find back where I was. We just calculated the t, 1.138. Okay. The alternate was greater than. All right, so I need the greater than probability. That's a one-sided test. So I need the right side, the right tail probability, and I'll show you how to do that. Okay, so what we're going to do, it's very easy. I go to StatCrunch, I click Stat, T-Stats again. We did this with the confidence interval. One sample with summary, okay, because I have summary information. I have the summary statistics, right? And I'm going to put in the sample mean, which is $45.26. I put in the sample standard deviation, which is $20.67, and the sample size of 20. And it's already going to have the hypothesis test checked, but instead of, I'm testing if mu is greater than 40, and usually at the 0 there, I change that 0 to 40. It has a not equal here. I change that to a greater than. And then I hit click, and there we go. So there's my p-value. Like I said, it's 0.1346. And here is the sample mean, S over the square root. Same stuff we had from the confidence interval, but here instead of the confidence interval, I get a test statistic, which we already calculated, 1.138, and a p-value. Okay, so those two things both come out of that. So feel free to use StatCrunch on your homework for Tuesday. Okay. Now, what can you conclude about the overall mean sales? All right, so is there enough evidence that the purchase is at least $40? Well, we have to ask ourselves, is the p-value less than 0.05? All right, I go 0.1346. That is almost 3 times 0.05. That is bigger than 0.05, so the answer is no, it's not less than 0.05. So we have the 3 things. we cannot reject the null hypothesis, fail to reject, or do not reject. It's not significant or it's insignificant, and we don't have enough evidence. There is not enough evidence. So $45.26, that is not far enough away from $40 for us to be convinced that the overall mean is over $40. So it's too close to 40 for us to be able to prove that the average of all purchases are over $40. Okay, so in summary, last week we learned the central limit theorem. If n is big enough and we have independent and representative sample, then the sample mean is normal with mean mu and standard deviation sigma over the square root of n, where mu and sigma, again, those describe the population. Like, what is everybody? The mean of everybody and the standard deviation of everybody. Okay. The standard error, we're going to use S as an estimate of sigma. So instead of sigma over the square root of n, now I have S over the square root of n. The confidence interval, you say, hey, okay, we're going to estimate mu with my y bar, so that we're going to estimate the population mean with the sample mean, and then I'm going to add or subtract a couple of these standard errors, and that'll be my confidence interval for the underlying mean. Right? And the test statistic is also a t-distribution, because when I use the standard error, I get a t instead of a z. So there's no z's in inference for means. All right, so I'm going to take my y bar that I actually got, I'm going to subtract what I'm testing, and I'm going to divide by that standard error s over the square root of n. Okay, so I wanted to show you one more example where we have data. All right, so occasionally on your homework, they'll have a little table. You know, you click it, open in StatCrunch, and then you get this table. So here's 12 times from a random sample that students spent in the lab. All right, so now I have data. I don't have summary information. I actually have the individual 12 individual times. All right, so it used to be the average time was 55 minutes. And somebody in the lab thinks, well, I think it's bigger now. So they took 12, they randomly selected 12 people, recorded how much time they spent in the lab. All right. So now to do this, I'm going to do StatCrunch. I'm going to do stats, t-stats, one sample with data. Before I do that, I should, though, check my conditions. Okay. So to check the conditions, I look and say, end and rep. Is it independent and representative of the sample? Well, it's random. So that means it's independent and representative. All right? And so then is the size big enough? So we have n is 12. So it's going to be okay as long as the histogram is unimodal symmetric, because that's a very small sample. 5 to 15. They call this nearly normal. It can be almost symmetric. Okay. So here's what I did. You can do in StatCrunch, and you're going to have to do this for the homework. They may say check the conditions, and you'll have to make a histogram. So you go to StatCrunch, and instead of hitting stats, which is what we've been doing a lot of, we're going to go back to graph. Remember, we did graph histogram. You select the column and hit submit, and this is what you get. So this thing right here is what comes out of StatCrunch when we first do it. And for some reason, even when the data sets are really small, StatCrunch does not accommodate and reduce the number of bins. I mean, for a very small data set, you should have at most 5. All right, so I just went back in. I said, hey, I want 4 of these instead of 5. I want to see if it's symmetric or not. So I just figured out, I said, well, it's the minimum value on this guy is 0, and the maximum is 140. So I thought, all right, let's divide that area in 4. So half would be 70, and half of that. So 35 should give me 4 bins, and it does. And so I just went back, I put options, edit, and I just changed, not the number of bins. I changed the width of the bins. So the bin width, instead of being here it's 20, so from 20 to 35. And now I got 4 bins, and now we see. So it's very slightly skewed right, okay? It's not exactly symmetric, but it's close enough. This looks pretty good, right? It's near normal, you know. If this thing was, you know, maybe a little bit, and it's close enough. Close enough. It's not extremely skewed by any means. Okay, so once I know it's met the conditions, then I say, okay, let's run the analysis. So I'm going to do t-stats, one sample, but this time instead of with summary, I'm going to say with data, which makes my life a lot easier. And then I select the column minutes, okay, and I click on hypothesis test, and I change the test from 0. I put this 55 in here, all right, because that was because it used to be 55 minutes. I'm testing if it's different from that now as the time changed. So I leave the not equals in there, I run it, and here's my results. And I didn't know this before, but now I know that the sample mean, that the mean of the sample, so the average time that those 12 students spent was 63.25 minutes. This is the standard error, so this is S over the square root of n. We have 12 students, so that's whatever S is. It's the standard error. So degrees of freedom are n minus 1. There were 12 students, so 12 minus 1 is 11. And here's my t statistic. So t, this is my test statistic, is 0.988. I'll leave it like that. Okay. And then my p-value, we get another big one, is 0.344. Okay, so those come from here. So there's my test statistic and my p-value. And so I just talked more about that. All right. Now, if I recall, I go back and get what was my alternate hypothesis? Was that, I have to get really far back, don't I? U is greater than 40. The mean amount spent is at least $40. Okay. So the p-value, if the p-value is less than 0.05, I have enough, oh, there it is. I have enough evidence for this guy, only if the p-value is less than 0.05, but it's not, again, just like the other example. Oops. If the p-value is less than 0.05, then we have enough evidence for the alternate. If not, I don't say that the mean is 40. I don't know what the mean is. But we don't have enough evidence to say it's over 40, right? So then I get on my knots. It's not significant, you know, not significant. I can't reject the null hypothesis, and there's not enough evidence to say the mean of all sales is greater than $40. So this is inconclusive. When I get a big p-value, it's like I don't know what's happening. Okay, so I don't know what the mean price is. It's probably around $45. Right? Now, what if I want, normally, and like I said, most software gives you the test and the hypothesis test. All right, so let's get a confidence interval for this. All right, we don't know what the mean is, but what do we think it is? So we can go back in here. Right. Oops. There we go. Oh, by the way, there's the p-value, and there's a little drawing of the p-value. All right, here's our t is 0.988. There's negative. This is a two-tailed test because our alternate was not equal to. We have the area to the right of 0.988, and because it's two-tailed, I also get to the left of negative 0.988. Right. Again, do not look up these in the standard normal table because the means, if the test for the means, it's not normal, it's a t-distribution, it's a different distribution. Okay, so if I want the confidence interval, I already put in, you know, I've already done some of the stuff. So if I just like click options edit, I can change it from a hypothesis to a confidence interval. Just rerun it, okay? And I get these. So here's my confidence interval. Here's the lower limit and the upper limit. All right, so we're 95% confident that the average time a student spends in the lab is between 45 minutes and 82 minutes. All right, now I know you already figured it out, but, all right, we said 95% confident the mean time in the lab is between 45 minutes and 82 minutes. from that confidence interval, can I tell if there's enough evidence to say that the mean is not 55 minutes? So think about that. Let me give you a few seconds to think about that. So does that interval tell you the mean is not 55 minutes? Okay, and the answer is no. And the why, which is important, all right? Between 45 and 82, these are reasonable values. These values are reasonable guesses at what mean is. At the true mean. Okay? And 55 is in there. So 55 is a reasonable possibility for the mean time. Therefore, we can't, this interval doesn't say, hey, well, it's definitely not 55. Okay, so the answer is no. And this is because the test value, 55, is in the interval. So if it's in the interval, I can't disprove it. All right. Well, that's all I have for you. Good luck on your homework. Email me with questions, and I'll see you guys on Tuesday.